Bismillahirrahmanirrahim. In this last portion, E of Lecture 8, we will describe one of the most important applications of probability models, and that is the random sampling. We are often in a position where we need to find out something about very large populations, and it is impossible to go and collect information for every single person. For this purpose, we take surveys which take a small sample and try to get information about the bigger population. In particular, we will be discussing voting behavior. How do people who take sample survey opinion polls find out about what will happen in the election? These are called pollsters. So even in the best case scenario where everyone knows who is going to vote, who he is going to vote for, and everyone is decided, it is impossible to go and ask everyone. So we must use a sample, a small number of people, and guess at what is happening in the population on the basis of our sample. Samples can often be wrong. I can describe my personal experience when I was an undergraduate at MIT in December '72, and there was an election going on for Nixon versus Brown. And Brown was elected in Massachusetts, where I was, and nearly everybody I talked to was voting for Brown. So on the basis of my own personal sample, I thought that Brown was going to win. But actually what happened in that election was that Massachusetts was the only state in which Governor Brown won, and 49 states were taken by Nixon in a landslide election. So my personal sample was highly non-representative of the big picture. This was my personal example, but Friedman's textbook on statistics gives many cases of elections in which the polls, which are professional, sophisticated, they have come to the wrong conclusion about the election. Most recent example being Trump versus Clinton, where the polls overwhelmingly predicted a win for Hillary Clinton, but actually Trump ended up winning. So the question is, how do we predict election results? By taking a survey, and in particular we will see that random sampling has a very important role to play in this. The most important problem is one of finding a representative sample. In the most recent elections in 2020 in USA for Trump versus Biden, about 155 million people voted. So it's not really possible to go and ask 155 million people who you are going to vote for. It's just too expensive. So how can we predict the outcome? We take a smaller sample. Gallup uses about 3,000 people. How can you learn what 155 million people are going to do by studying 3,000 people? This is seems to be very strange, very surprising, almost impossible. The point is that if we take a sample of 3,000 and pretend that this is the population, the proportion of Biden voters in our sample of 3,000 should be like the proportion in the full population. So basically the issue is, how can we choose a sample inside of which the proportion of Biden voters is similar to or close to the proportion in the whole population? Can this be done? A very surprising answer to this question is that if we can do random sampling, this will tend to create representative samples. And now we discuss how this happens. In previous lectures, we have criticized Fisher for being a racist and a eugenicist. But in this particular example, random sampling was the genius of Fisher to see that random sampling could create representative samples, and this is superior to all systematic methods. It seems counter to sense that using intelligence to pick accurately a sample doesn't work as well as just letting a lottery decide who should be chosen. So another thing about random sampling that is very surprising is that the size of the population doesn't matter. It is the size of the random sample. So even if you have a population of 100 million people, the sample accuracy depends only on the size of the random sample. So we will see how this works. It's very important to understand that there are two senses of the word random, and they are often confused. In the standard English language sense, random just means without any systematic procedure or pattern. So if I just close my eyes and point at somebody, then I have selected him randomly. But that's not the sense in which statisticians use this word. There is a technical statistical sense. If you want to pick one person at random from a population which has 1,000 people in it, then you must use a procedure such that every single person has an equal chance of being selected. That is, every person must have a probability 1 over 1,000 of being selected. This is actually very difficult to do in practice. To understand this better, how can we achieve, what procedure should we use to actually achieve this result? So first we must make a list of 1,000 names, and then we use a randomization mechanism to pick one of these names in such a way that the mechanism has equal probability of picking any one of the 1,000. So there are actual practical procedures we can do. There are random number generators on computers which generate something which is called pseudo-random. These have been tested so that it has been shown that every number they produce is spread out among all of the choices in a roughly equal way. But still, the starting point matters, and the starting point can determine the sequencing. So one of the things you can do is to use a real time counter which is counting in milliseconds and start at some time. So this number, the initial choice, will be random, that is the seed, and then based on this seed further random numbers will be generated. So there are some many possibles ways to generate random numbers. The demonstration that the person was chosen at random is always within a model and never actually, never empirically, because it involves showing that even though we chose X, every other person had a chance of being chosen. This is something which we can never observe, but we can get some evidence by looking at the procedure. Now we assume that random sampling can be done, and we discuss the properties of these random samples on the basis of our theoretical probability models. So here's what a random sample looks like. Suppose we have 81 million Biden voters and 74 million Trump voters. So we must select from this entire population of 155 million in a way that all of the 155 million have an equal chance of being selected. Now, this is hard to do, and how it is done is discussed separately. But suppose that we have an access to a list and we have access to a randomization procedure which picks one person out of this population at random. Let's call this person S1. This is the first sample. So now, if all people have an equal chance of being selected, then let's label Biden voter as 1 or a success and the Trump voter as 0 or failure. Then the probability that this S1 equals 1, that means that we select a Biden voter, is 81 divided by 155. And the probability that we select a Trump voter is 74 divided by 155. Now we consider a sequence of random choices. We pick the first sample at random and the second one, and so on until n is chosen. N is like 1,000 or 3,000 or whatever the size of sample we want to choose. Then this is the random sample of size n. It is a sequence of ones and zeros. 1 represents a Biden voter and 0 represents a Trump voter. And suppose we count the total number of Biden voters in the sample, then this count X is binomial with n trials and 81 over 155 probability of success. So this model satisfies our binomial theory probability model, and so we can apply the results from the binomial distribution theory. So how do we use this probability theory model? We look at the large sample confidence intervals to make predictions. And so basically the prediction is based on the SD, the standard deviation, which is defined as square root of p times 1 minus p divided by square root of n. Let's look at this particular example. So here the Biden voters are about 52.2% and the Trump voters are 47.8%. So we multiply these two probabilities and take the square root, and that's come out to be very close to 50%. And then suppose we have a sample of size 3000, so we take the square root, and that's about 54 over 77. So when we take the SD, that's 0.0091, which is 91 parts in 10,000, or roughly 9 in 1,000. That's 9 in 1,000. That's slightly less than 1%. So now, according to the confidence interval theory, if X is the number of Biden voters, then with probability 99.7%, X divided by N, or the proportion in the sample, minus the true proportion in the population, which was 52.2%, this difference will be within plus or minus 3 SDs with probability 99.7%. So what is 3 SD? 3 times 0091 is 2.7%. So basically what we're saying is that if we take a random sample of size 3000, the proportion of Biden voters in this sample will be different from the true value 52.2% by less than 2.7% most of the time, with very high level of confidence. So basically we have a 2.7% error margin between the sample proportion and the true proportion. So here's the key result, that if I take a random sample and I look at the proportion of voters in my random sample, the difference between this proportion, the proportion within the sample, and the true proportion will be within 2.7% with 99.7% probability, with a very high degree of confidence. This is true before the poll. Similarly, if I want to have more accuracy, I can look at 2 standard deviations. That's about 1.8%, and that will be the accuracy of my sample with 95% probability. These 2 statements are true before the poll. One more interesting thing is that this accuracy depends only on the 3000. The number of 155 million didn't enter into these calculations. So the size of the population does not matter. The accuracy only depends on the size of the random sample. Now, after the poll is actually done, then these probability statements turn into confidence statements. I have made a prediction. Either the prediction is true or it is false. The true proportion falls within my confidence interval or it does not. The probability is either 100% or 0%, and not these 99.7 and 95%. But at the time that I'm making the prediction, I don't know whether or not it's true. So this will be a subjective probability or a confidence level, but depending on other information I might have from other sources, I might adjust this subjective probability or confidence level. So here's a table of how standard deviation behaves as a function of n. At n equals 100, standard deviation is 5%. At 500, it's 2.2%. At 1000, it's 1.6%. At 5000, it's 7 parts in 1,000. And at 50,000, it's 2 parts in 1,000. So it goes down with sample size, roughly in proportion with 1 over square root of n. So what we can see is that basically the standard way to use SD is to look at 2 standard deviations as the measure of accuracy, which gives us 95% confidence. So with a small sample of only 100, we can predict with accuracy of about 10%. That's 2 SDs. With more like 5,000, we have accuracy of about 1.4%. That's 2 standard deviations and 95% confidence. With the sample of size 50,000, 2 SDs is 0.4% or only 0.5%. So with 95% we can probability or 95% confidence, we can get within 0.5% of the true proportion. So basically, if the race is very, if the numbers are very different in the population, we can get accuracy with very small sample sizes. But if the race is very close, if the two proportions are very close, then we need large samples to get the desired accuracy. And the size of the total population is irrelevant to this. Only the size of the sample matters. We have discussed the theory of how accurate random samples are. Now we look at the reality. How does this work in real life? So here's a record of predictions by Gallup compared with the actual results and the errors. So one of the things that is clear is that the errors are much larger than the theoretical predictions. It is not true that the 99% or 95% confidence intervals nearly always happen. In fact, the errors are substantially larger than the theoretical values, but nonetheless, the errors are small. We do get accurate results most of the time. And also, one of the advantages of random sampling is that the size of the sample has gone down drastically. Initially, when it was started, they used samples of size 50,000, but now they are using samples of size only 3,000. And they have also learned a lot more about polling from the experiences and by making mistakes. When a large mistake is made, people go out and analyze why this mistake was made, and then they try to prevent it in the future. Some of the things which we have learned is that, first of all, there is the technical difficulty of picking a random sample. There's no list of all the 155 million voters that we can use in order to make a random choice as dictated by theory. So compromises are used. Multi-stage cluster sampling method, which is described in the notes for this lecture. And even after you select the perfect random sample, there are issues of selection bias, which doesn't apply to random sampling, but to other methods of sampling. There is non-response bias. If you go and ask people and they don't say anything, if you make a telephone call and there is no response, then there's response bias, which means that somebody responds but doesn't give you the right answer for various reasons. In addition to these sources, there's the problem that the vote will take place in the future and you're asking some months ahead of this time. So the question is, who will actually, a person might express a preference that he's planning to vote for Biden, but he might not actually go to the polls. So who will actually go? And then there are people who are undecided. They don't know, they haven't made a decision by the time the poll is being done. So you can't predict what they will do. And then there are people who switch, they change their minds. They will decide for one thing and they decide for others. So all of these sources of inaccuracy are reflected in the errors, which are in addition to the theoretical accuracy of the random sample. Friedman provides many real-world examples of where the polls came to a dramatically different result from the actual elections. And since his book, many more examples have been discovered, have occurred. In particular, the Trump versus Clinton example was a really striking one, in which nearly all of the polls predicted a strong win for Clinton and a loss for Trump, but actually Trump ended up winning the election. So basically, forecasting future is inherently difficult. Probability models give us some edge, but they don't give all the answers. And there is radical uncertainty which prevails, in the sense that we can't really tell what is going to happen. And this is a very different model of reality than the rational choice making model, which is commonly used by economists, which assumes that the future is known at least to within the probabilities. So actually we don't know what's happened and we don't know the probability of what will happen. And this makes a huge difference in terms of the theory of decision making under uncertainty. So in terms of concluding remarks for this lecture, we would like to reassert that random sampling is one of the most important applications of probability to the real world. The theory of Monte Carlo is another application which is based on the same type of results as random sampling. Surveys of public opinion without random samples are not very reliable because they are subject to lots of different kinds of biases. On the other hand, random samples, truly random samples, are very difficult to get. Even if you have a theoretically perfect random sample, the surveys have many other sources of errors in the real world, and we live in a world of radical uncertainty. And so very often when we take action, we do so without knowledge of what will happen and without knowledge of consequences, and we act with very poor, very low quality information. And this means that we must rely a lot more on intuition and much less on rational decision-making theory